Hi everyone, I'm Cheryl. In this problem, we're going to be analyzing and graphing the function f of x equals 2x minus 4 sine x on the interval from 0 to 2 pi. And then we're going to use a graphing utility to confirm our results. All right, there's quite a bit to do here, so we're going to start out by looking at some intercepts. First of all, let's consider the x-intercepts of this function. We know that you find x-intercepts by setting y equal to 0. So 0 is going to equal 2x minus 4 sine x. Looking at this equation, I can add 4 times the sine of x to both sides and get 4 sine x equals 2x. And I can do one more thing, simplifying a little bit, and write this 2 sine x equals x. Now, unfortunately, this is a fairly complicated equation to solve for x. You can see, I think, that if x equals 0, the sine of x is 0, and so I'll have 0 equals 0. So 0, 0 is an x-intercept. But there's another x-intercept, and this one's much harder to find. If you take a look at the graph of 2 sine x and the graph of y equals x, this line intersects the sine curve in 2 locations. One of them is 0, 0. The other one, if you use a numerical method, you can find out that it's going to intersect at approximately 1.9. So I have another x-intercept at 1.9. And again, there are going to be other spots, but I'm only interested in what's happening between 0 and 2 pi. So between 0 and 2 pi, these are the only 2 x-intercepts. Okay, let's do y-intercept. This one's a little easier to look at. So a y-intercept happens when x equals 0. So we're going to find f of 0. F of 0 is going to be 2 times 0 minus 4 times the sine of 0. This is going to be 0 minus 0, and that equals 0. So our y-intercept happens at 0, 0. This should not be a surprise because with an x-intercept at 0, 0, the origin will always be both an x-intercept and a y-intercept. Okay, let's move on and talk about asymptotes. Right? So the first thing I'm going to talk about are vertical asymptotes. Now remember, vertical asymptotes, your function will not be defined at those locations. And if you look at your function, 2x minus 4 sine x, that's going to be defined for all values of x. And again, we're only interested between 0 and 2 pi, but it's defined everywhere. So there aren't any. So there are no vertical asymptotes. All right, what about horizontal asymptotes? Well, to find a horizontal asymptote, we want to take the limit as x approaches infinity of our function, but also as x approaches negative infinity. And you can do this calculation. However, again, notice I'm only interested in what's happening between 0 and 2 pi. So I'm not really terribly interested in what happens as x gets very, very large or as x gets very, very small. If we remove this restriction and we did take the limit, it's going to be infinity and negative infinity anyway. So there are no horizontal asymptotes for this graph either. Okay, so I've got a little bit of information. But now I really want to get into the when is my function increasing? When is it decreasing? What's the concavity look like? In order to answer these questions, we need to look at derivatives. So we're going to start by taking f prime of x. F prime of x is going to be 2 minus 4 cosine x. And we're going to be looking for critical numbers. Critical numbers happen when the derivative is equal to 0 and when it does not exist. Well, when does that derivative equal 0? 2 minus 4 cosine x equals 0. If you add 4 cosine x to both sides, you get 2 equals 4 cosine x, and cosine x equals 1/2. That's going to happen at pi over 3 and 5 pi over 3. Again, it'll happen at many other locations, but I'm restricting myself to look for answers between 0 and 2 pi. When does the derivative not exist? Well, 2 minus 4 cosine x exists for all values of x, so I don't get any critical numbers by looking at when the derivative does not exist. Okay, so what does this tell me? Well, I need to find a little bit out about when is this increasing or decreasing. I like to make a little sign chart to help me with this. So I'm going to draw a sign chart. I'm going to put 0 and 2 pi on my sign chart because I'm restricting myself between those two numbers, and I'll mark down my critical numbers, pi over 3 and 5 pi over 3. I also like to write why they're critical numbers above them. In this case, they were critical numbers because the derivative was 0. Now we're going to do some test points. Okay? So pick any point that you like between 0 and pi over 3. Okay? Any point between those two numbers will do. Pi over 6 is easy, so we'll try that. We're going to plug pi over 6 into the derivative to see what the sign is. The cosine of pi over 6 is root 3 over 2, so we'll end up with 2 root 3 for this piece, and 2 minus 2 root 3. That's going to be a negative number. Again, I don't care what the actual value is, just whether it's positive or negative. Now pick something between pi over 3 and 5 pi over 3. Again, any number between those two values will work. So let's try pi over 2. The cosine of pi over 2 is going to be 0, and 4 times 0 is 0. 2 minus 0 is a positive number. And finally, pick something between 5 pi over 3 and 2 pi. 11 pi over 6 will work well. So again, we'll have 2 minus 4 times the cosine of 11 pi over 6. And if you do that calculation, it turns out to be a negative number. Okay, so that gives me some information about the first derivative, which will lead to information about increasing and decreasing and increasing and decreasing and relative extrema. Now we're going to look at concavity. Concavity, you need the second derivative. So let's go ahead and look at the second derivative. Okay. My first derivative is 2 minus 4 cosine x. So my second derivative will be 0 minus 4 times a minus sine x, which simplifies to 4 sine x. Again, I want to know when this second derivative is 0 and when does it not exist, because I'm finding critical numbers. So when does that equal 0 and when does that not exist? Okay, well, 4 sine x equals 0 when the sine of x equals 0. The sine of x equals 0 at 0, pi, and 2 pi. Again, many other spots, but because I'm only interested in what happens between 0 and 2 pi, those are the only answers in that range. So 0, pi, and 2 pi. Again, my second derivative is just 4 sine x. It's defined everywhere, so I don't get any critical numbers from that calculation. All right, I'm going to create a little sign chart for this one, just like I did for the first derivative. So when I make my sign chart, I'm going to start at 0, end at 2 pi, and I'm going to mark down all those critical numbers. Well, I have 0 and 2 pi marked as critical numbers. The only additional one I have is pi. And I know that the second derivative equals 0 at all of those locations. All right, it's time for the test points. So pick any number that you like between 0 and pi. Pi over 2 works well. Now remember, this time I'm using my second derivative, so I need to plug it into the second derivative. The sine of pi over 2 is 1. 4 times 1 is a positive 1, so that's a positive value. Pick any number you like between pi and 2 pi. Okay? 3 pi over 2 works well. The sine of 3 pi over 2 is a negative 1. 4 times negative 1, that's a negative value. Okay? So now I've created this little sign chart for myself. Well, why did I need these? Well, I need to get all of this information together now to look at the graph. This is a lot of stuff, so it's nice to have a table to help me organize all my information. So let's go over to this table and notice that I have columns for f of x, f prime, f double prime, and then a column to talk about some characteristics. All right, well, what I want to do is break down my graph into certain intervals. And what intervals am I going to use? Well, I'm going to use all the intervals that were broken up by all of the critical numbers and the endpoints that I started with and ended with. All right, so I'm going to start out with the value x equals 0 because that's where I'm starting my graph. The next critical number that happens is pi over 3. So I'm going to look at the interval that goes from 0 to pi over 3. And then I'm going to check out what happens at exactly pi over 3. Well, after pi over 3, the next critical number that happens is pi. So I'm going to look at values between pi over 3 and pi. Then I'm going to see what happens at pi. Next, I'm going to look for values between pi and my next critical number, which is 5 pi over 3. Then I'm going to check out what happens at exactly 5 pi over 3. Finally, or not finally, but the last interval is going to be the interval from 5 pi over 3 to 2 pi. So let's see what happens between 5 pi over 3 and 2 pi. And finally, what happens at exactly 2 pi, which is my endpoint. Okay, I have a lot of information here, a lot of different intervals. Now I need to start filling in the next 3 columns. The first column, notice, is the column for f of x. I'm trying to find the y value at all of my important points. My important points are the endpoints and these critical numbers. Right? Now you may need to pull out a calculator to do some of this number crunching, but notice what happens here. I want to find what the y value is when x is 0. So I'm plugging it in to the original problem. Okay, so that's going to be 2 times 0 minus 4 times the sine of 0. That one you could probably do in your head. That's 0. The next few are going to be a little more complicated. I want to find out what happens when x equals pi over 3. So I want to calculate 2 times pi over 3 minus 4 times the sine of pi over 3. And when I do that, I get a negative, approximately negative 1.37. I'm going to do exactly the same thing for pi. I want to plug pi into the original problem. So I'll have 2 pi minus 4 times the sine of pi. Now the sine of pi is 0, so it's really just going to be 2 pi. And if I'm going to use decimal approximations for that, that's going to be about 6.28. I have to plug 5 pi over 3 into my function. So 2 times 5 pi over 3 minus 4 times the sine of 5 pi over 3. And that's going to be approximately 13.94. Okay. One more, I need to plug in 2 pi. The sine of 2 pi is 0, so 4 times 0 is 0, and I'll just have 2 times 2 pi, so that'll be 4 pi. So the decimal approximation of that is going to be 12.57. Okay, those are all going to be very important points that I'm going to plot on my graph. However, the next thing I want to do is go ahead and get information about my first derivative. The first derivative tells me when it's increasing or decreasing. So let's look at, instead of points, let's look at the intervals. Between 0 and pi over 3, I can tell my first derivative is negative. So I'm just going to transfer that information. The next interval I'm looking at is pi over 3 to pi. Now notice I don't have this written, but it all fits right inside of the interval, which I know is positive. The next interval is between pi and 5 pi over 3. Again, I don't have that interval actually marked, but it all fits right inside this middle interval, so I know it's positive. The last interval I'm looking at is from 5 pi over 3 to 2 pi, which is this piece, and I can see that my first derivative is negative on that interval. Okay, now I'm going to do exactly the same thing, but I'm going to be using the sign chart that I created with my second derivative. So let's look at the interval from 0 to pi over 3. I don't have that exactly marked, but it all fits exactly inside that first piece. So I know that my second derivative is positive on that interval. From pi over 3 to pi, again, it fits right inside, so I know that that's positive. All right, so next I need to start with the interval from pi to 5 pi over 3, and notice that fits right inside this one, and so it's going to be negative. The last interval to consider is 5 pi over 3 to 2 pi, which is going to fit right inside this interval, so I know that the second derivative is negative. Okay, what does this tell me? Well, it tells me that on the interval from 0 to pi over 3, my graph is decreasing and it's concave up. The first derivative tells me increasing and decreasing information. The second derivative tells me about concavity. This next interval, because the first derivative is positive, it tells me my graph is increasing. Because the second derivative is positive, it tells me my graph is concave up. On my next interval, first derivative is positive, that tells me it's increasing. Second derivative is negative, so it's concave down. My last interval, first derivative is negative, that tells me it's decreasing. Second derivative is negative, that tells me it's concave down. All right, so that's telling me what's happening on all the intervals. What about these ordered pairs that I'm working on? Well, let's take a look at, first of all, pi over 3 and negative 1.37. Notice that it changes from decreasing to increasing. So if it's decreasing and then increasing, you must have a relative minimum. At the point pi and 6.28, notice there's no change in increasing and decreasing, but there is a change in concavity. That makes it an inflection point. At the point 5 pi over 3 and 13.94, notice there's a change from increasing to decreasing. So if it increases and then it starts to decrease, that's going to be a relative maximum. At 0, 0, that's an endpoint, as well as at 2 pi. So now I have all the important information about my graph and exactly what the shape is. We now need to take all the information in the chart and transfer it to an actual Cartesian plane. So let's begin by transferring these important ordered pairs onto my Cartesian plane. So I know that the point 0, 0 is on my graph. I also know pi over 3 and minus 1.37 is on the graph. So that's going to be right about here. Pi and 6.28, so that's going to be right about here. 5 pi over 3 and 13.94, so that's going to take me almost all the way up to 14. And the point 2 pi and 12.57, so that's a little lower, right about here. Okay, now that I have those important key points, let's see what's happening on those intervals. I know that between 0 and pi over 3, which is taking me from this point to this point, my graph is decreasing and concave up. So it's going to look like this. Between pi over 3 and pi, my graph is increasing, but it continues to be concave up until I hit my point at pi. Between pi and 5 pi over 3, I continue to increase, but now I switch to concave down. And then from 5 pi over 3 to 2 pi, I decrease, but I'm still concave down. All right, let's take a look at what I have. I've put in all the increasing, decreasing, and concavity, but notice at pi over 3, it looks like I have a relative minimum. Well, that's exactly what I'm supposed to have. At pi, I had a change in concavity from concave up to concave down, and notice I had that marked as an inflection point, so that works as well. It also appears that I have a relative maximum at 5 pi over 3, which is exactly what I was expecting to happen. So I've transferred all the information from my chart to my Cartesian plane, and I have a nice picture of the graph. The last thing we need to do in this example is to use a graphing utility to verify my result. So if you enter the original problem, 2x minus 4 sine x into your graphing utility and graph it. Now, because of the restriction of x between 0 and 2 pi, you're going to want to adjust your window. And the nice thing about graphing this ahead of time by hand, I have a pretty good idea what my window should be. Something between 0 and 2 pi would work well. And also, I'm going to want to have my y values go somewhere between anything, say, from -2 to 14. So if you want to expand that a little bit and go from -4 to 15, say, that would work well. And when you go ahead and graph, you see that the graph looks just like what we found using just the calculus. I hope that was helpful. Thanks.